Let's take a look at a shear and moment diagram problem where we're asked to sketch the V and M diagrams for a simply supported beam that has a concentrated load of 200 pounds and a distributed load of 100 pounds per foot. Before we start, it might help to refresh your understanding of shear and moment equations. Let's solve this. Step 1, R is the area underneath that load curve up here, which is 4 feet times 100 pounds per foot, or 400 pounds. And it will act at the centroid of so we'll place the 400-pound load there, just temporarily, so that we can do the free body diagram. Our free body diagram, we have a support reaction here at A, and a support reaction over here at B. And we can do some of the moments about A, in which case we have 200 pounds times 2 feet plus 400, our equivalent load, at 6 feet has to equal B at 8 feet, which tells us that B is 350 pounds. And if we do some of the forces in the y direction, we find that A plus B acting up has to equal 200 plus 400 acting down, and A will be 250 pounds. So we have 250 here and 350 over here. And with that, we're ready to draw our V and M diagrams. Okay, to start our shear and moment diagrams, when we're doing a shear diagram, shear is force. So note, any applied forces cause shifts in V. What do I mean by that? If we imagine that this beam extends further out past A, there's no load out here, so we'd anticipate that there'd be no V in this region. When we reach the 250, it would generate a sudden shift of 250 in our V diagram. There's no additional loads here, so there's no change in V, so that would be a constant for that regime. Now we reach this 200 pounds. So the 200-pound concentrated load would create a sudden shift here by 200. And again, there'd be no change. So that would be at now 50. When we reach this point, let's ignore it for now. What's going to happen when we pass this location? We're suddenly going to see the 350 uncovered, so we'd anticipate that there would be an upward bump of 350. So we'd need to start here so that once we went beyond this location, we'd be back to having no loads again. So if X continued off the beam, we're back to no load. So these are called end conditions. And they're very useful when you're doing a quick sketch, because by knowing this end condition, I now know this function has to somehow connect itself between those two dots. So how does it connect itself? Well, again, recall we integrate as we're moving between each of these. So it's going to increase by one order of complexity, which up here we have a y is equal to ax to the 0 form. So we'd anticipate this would be y is equal to ax to the 1, which is a linear function where that has a constant slope up here, right? So it has a slope of 0. Now we'd have a slope equal to this value. So we'll have a linear connection between these 2 points. And recall that value here is negative slope down here. So this would have a negative 100 pounds per foot slope. Let's see if that's true. We're going 4 feet, so we should lose 400 pounds from here to there. And we're starting at 50 and ending up at 350. Indeed, this is 400 pounds, which is also the value for R. Recall that area here is changed down there as well. Remembering those relationships is useful when doing quick sketches. Now we'd like to have this crossing point. Anytime we have our functions crossing 0, those are important. And this is fairly easy to find. The amount of area that we uncover up here has to undo this value of 50. Remember that area is negative change below. So let's define a new variable u, which I'll use just to measure from here. So we can say then that u times 100 pounds per feet has to equal 50, which is the amount that we have to offset this by. And we find that u will be 1/2 the foot. If we label this, this is 2 feet, 4 feet. This would be 4.5, and this would be 8 feet along the x. And there we have our shear diagram. And keep in mind that the values for this shear always point towards the axis internally. So if we want to know what direction they were acting. So there we have our shear diagram completed. Now let's start the moment diagram. When we're sketching a moment diagram, you'll often wonder how much room do I need below for the negative moments that I might have. And there's an interesting way to keep track of that. It's by deflection. If the beam is bending, point of inflection, you'd have m equal to 0. And happy faces are caused by positive moments. If we look at this beam, for this load configuration, I can see the beam is going to deform something like that, in which case it's going to be quite happy over the whole region, and I anticipate this being a curve that looks like that. If this support were further in, it might curve like that, in which case this would do something like that down here. So this moment curve should have all positive values. Now continuing with our area slope method, the area here, which I'll call area 2, is 250 times 2 feet, which is 500 feet. And that's equal to delta m for that same region. So again, end conditions are 0. There are no applied moments or couples. So I anticipate this to start at 0 and end at 0. And for this region, we know that we have a 500 foot-pound change. So let's show that here. I know the end point will be at 500. And now the question is, how does it get there? Well, if we look up here, that value is the slope below, and note that it's a constant. So I anticipate this to have a straight linear function in that region. Now to get from here to here, we'll have A3, which is this area right there. And that'll be 50 times 2. Again, this is 2 feet. So we have 100. This would be foot-pounds. So from here to here, we'll increase another 100. Notice it does not tell you the value. It tells you the change in M for that region. And we have a linear zero slope up here. So this would be a linear slope of 50, which gets us to here. This 0 up here is important in that that represents a max value, the moment. And this little area will be 1/2 times 1/2, which is how wide that is, times 50, which would be 12.5. And that tells us that we'll increase by 12.5 additional foot-pounds. And we'll do it with a curve. Now this curve could be concave up or concave down. And we'll know because the value here is the slope below. So we start with a steep slope that decreases to 0 slope. So since the slope is 0, that means we are going to curve like that to meet our final end condition. So if we finish labeling this, we have 600 foot-pounds of moment there. And at the peak, we have 612.5 foot-pounds of moment acting at 4.5 feet. A sketch is a rough representation, but we do want to label all the peaks, the maximums, and the 0 crossing points, because they're what's important. Our beam has a peak moment of 612.5 foot-pounds, and it experiences a peak shear of 350 at the right hand support. To solve for the moment, we need to take a cut. The distributed load, X. So the free body diagram of that cut, and it has a range of 4 less than 0 equal to X. So there's the domain for that. We have 250 acting up here. We have 200 here. And we have a piece of the distributed load, but not all of it, that we've uncovered. And that's still 100 pounds per foot. And we're located, our cut is located at distance X out to here. So this distance that we are inside the distributed load would be X minus 4. Right there. So recall the standard convention here. A downward acting is a positive V, and internally that will be considered a positive M. We'll do sum of the moments about the cut equal to 0, in which case we have a plus M minus, and I start from left and work my way towards the right. So we have 250 acting at a distance of X away, so minus 250 X. Here we have then plus 200 And the distance would be x minus 2. And recall we're reaching out from there. And then this distributed load. Now to know what the distributed load is doing, we need to know what its R is. I'll call it R prime because it's not all of it, it's part of it. And it's the area uncovered, and it would be x minus 4 times 100. And to take a moment, we need to know its location, and that's at the centroid of this uncovered region. Now, since this is a rectangle, we know that's right in the middle of that. And it's also positive. So we have R prime times its distance from the cut to R prime. And that distance is right here. So it's half of x minus 4. This would be x minus 4 on 2. But keep in mind that R prime is x minus 4 100. So this term becomes 100 times x minus 4 times x minus 4 on 2, or 50 x minus 4 squared. Now don't take that apart, don't expand that, leave that like that. And with that we have our answer. The moment, this is all equal to 0. So the moment is equal to 250x minus 200 x minus 2 minus 50 x minus 4 squared. Being able to find the moment at a specific location is very useful. If you're trying to determine the deflection of that beam, you need the moment in the region in order to start that computation. So sketches are useful, and also being able to take a moment at a specific location is very useful. Thanks for watching.